In this chapter, we're going to learn dense estimation. So in pattern recognitions, all the algorithms implicitly or explicitly, the algorithms do dense estimation. That's what we want. Okay. And then there are a couple of approaches. So in this chapter, we're going to learn a couple of methods, dense estimation methods. So first, we'll talk about what the dense estimation is, and then basically, we have a couple of different approaches, parametric method approach and non-parametric and semi-parametric method. And then in the parametric method, we're going to learn what parameter estimation first in general, and then we will learn maximum likelihood estimation, which is one of the most popular dense estimation algorithms for parametric method. And as a non-parametric method, we're going to learn the kernel dense estimation and k nearest to neighbors. And as a semi-parametric method, we'll talk about mixture of Gaussian. And before talking about the dense estimations, we have to talk about why we need a dense estimation. Okay, so let's compare vector and distribution. For a data sample, we need a vector representation. Okay, so when we have one data sample, the vector is perfect way to represent the data sample. And when we have many data samples, then the vectors, yes, we can use vectors to represent all these samples, but it's hard to understand the data samples. So in that case, we need a distribution of the samples to understand the data set. So as an example, if you take an exam, then you got a score X. Okay, and usually if we take just one class exam, then we have one score number, which is a scalar. And then how do we know how good your score is? Let's say you got the 70. Then is it a good or bad? It depends on the distribution. If there are lots of students with 80, and if you get the 70 here, then your score is not quite good. But if the distribution looks like this, then your score is quite good. So to understand the samples, then we need the distribution. So that's why we want to estimate the density or distribution. Okay, now let's talk about the density estimations. So density estimation is an estimation of an underlying probability density function P of x based on the observed data and samples. Okay, assuming that the observed data are random samples drawn from the density function. This is quite important assumption. So all these data samples are coming from one unknown density function. So this is identical distributions. X1 is coming from one density function and x2 is coming from the same density function randomly. Okay, so we have n random samples from the same density function. This is a strong assumption here. And with density estimation, we can understand the population. Okay, so for example, if we have some distribution of the age in our populations in our country, then we can understand the population in terms of age. Okay, if we have a distribution of a weight or distribution of height, then we can understand the population in terms of the height or the weight. Again, if we know the density of population, then we can say we know the population. And then the density can be used for classification. In this, we talked about the unsupervised way. So there's no labels. We have bunch of samples. Then if we estimate the distribution, then we can understand the data samples. And if we have labels, then we can use this density estimation for classification. Given the labels and the data samples, then we can estimate the class conditional density P of x given C sub k. And then we can use the base rule to find this. P of ck given x is what we want for classification, right? And then this one can be written like this. So this is a prior distribution for the class. So if we have no idea about this one, then we can use simply the uniform distribution. And this one is coming from this density estimation. So which means, when we have lots of samples, we have class 1 and class 2. Then we gather all the samples from the first class and then we do some density estimation. That's what P of x C sub 1 means. And then from this, we can get P of x given C2. Okay. Simply is basically the same as just unsupervised density estimation. Just we have one condition here. When we classify one sample, we need the P of C1 given x and P of C2 given x, etc. So P, CK given x. So as long as we know all these probability, then we can see which class has the highest probability. Then we can classify it to that class. And in this case, the constant is nothing. So as long as we can compare this one and this one, these ones, then we can classify. So if you look at this equation, then if we don't have any prior information, then we can use a uniform distribution. So this probability is equal to all the cases. So we can cancel. And P of x is the same for all the classes. So we can cancel. So actually this probability is proportional to this. So as long as we know this probability, then we can classify with this probability. Now we want to talk about some different approaches for density estimation. First one, parametric method. So parametric method means we assume one functional form, and then we estimate the parameters in the functional form. And by estimating the parameters, we find the optimal function there. For example, if we assume that the functional form is Gaussian, then to define a Gaussian distribution, we have mean and variance as parameters. So as long as we estimate the mean and variance, then we can estimate the density. That's one good example of parametric method. And there is another method, non-parametric method. In this case, we have no assumption on the distribution. So we just estimate the density directly from the data. So as a simple example, we can think of histogram. So in the histogram, technically there are a couple of parameters, but it is different from the parametric method. Okay, these parameters are not the parameter of the function. But anyway, there is no real parameters. In this case, we don't assume anything about the distribution. So based on this histogram, these bars are histograms. And from these bars, we can have a density. So this is actually a density. Okay, and then the last one is a semi-parametric method. In this case, we actually extend the parametric method to more complicated, complex distributions. So it's very general, and it has more parameters than the parametric method. So we will focus on this parametric method and non-parametric method. First one, parametric methods. Before talking about parametric method, we have to talk about the parameter estimation. So parameter estimation is a more general kind of thing than just density estimation. So in estimation theory, we want to estimate unknown parameters from data. Okay. Let's assume that there are two parameters, theta, and then we have estimator that hat. So for example, if we want to estimate the height of this country, okay, then we have to measure all the height from all the populations. Then there is the true mean and the variance, but it's not possible. So there is a true parameter theta, but it is unknown and it's not possible to get because we cannot measure all people's height at the same time. So we have a true parameter theta, but it's hidden. But instead, we can estimate that parameter. For example, we can actually measure 1,000 persons' height, and then from that samples we can estimate the mean and we can estimate the variance. That's the estimator. So usually we use hat here. For true parameter, we don't have hat, we just use the theta. And then in the estimation theory, there are two important concepts. First one is bias. The bias is actually an error from assumptions in the learning algorithms. If bias is high, then it means the model is underfitting. And the bias is defined in this way. So this one is expectation of the estimator, and this one is a true parameter. If the bias is 0, then it is unbiased. If bias is not 0, then it is biased. And the next one is variance. Variance is an error from sensitivity to small fluctuations in the data. So if the variance is high, it means probably the model is overfitted. Okay, and the variance is defined in this way. So this one is our estimator, and this one is a true parameter, and then we take a square and then expectation. If this one is small, then that's good. In general, our estimator is supposed to be unbiased with the minimum variance. Okay, that's what we want. And we want unbiased and the minimum variance estimator, but there's a trade-off between these two concepts, bias and variance. So if we minimize bias, then sometimes we increase variance slightly, and when we minimize this variance, we increase bias slightly. So we have to find the best point. Sometimes the minimum variance with unbiasedness is not the solution sometimes because of that trade-off. Now let's talk about bias variance trade-off. Okay, so theta is a true parameter and theta hat is an estimator. And we can define an error like this. Is a square of the difference. And then if we unfold this square, then we got this. And then we can add this term and one more, and we can subtract this. So basically this is 0. So we didn't do anything here. We just added 0. And then we can rearrange these terms. This one, this one, this one here. And then the other ones will be here. Okay. Then if we look at this one, then we can rearrange into this term. And this one will be like this. Okay, then if we look at this term, this one is a bias, and this one is a bias square. And this one is the variance of that hat. Okay, so when we have this error is actually bias square plus variance. So there is a trade-off. This is total error, okay, and this one is model complexity. When we increase the model complexity, bias square decreases like this. Okay, and then while when we increase the model complexity, the variance increases like this. So when the bias is high, then probably this one is underfitting, and when the variance is high, probably this one is coming from the overfitting. Okay, and since the error is a sum of these two, then if we want to minimize this error, then the optimal model complexity is around here. Okay, because this error is minimized at this point. Now let's talk about maximum likelihood estimation. So MLE is actually a parameter estimation for density estimation. Okay, so we define a function as a distribution, and then we want to estimate the parameters of the distribution by maximizing a likelihood function. So likelihood function is actually probability distributions like this one, P of x given theta 1. So theta 1 is a parameters. So we have a functional form for this density function. Okay, for example, we can think of a Gaussian distribution here. Then the theta 1 and theta 2 will be a set of mean and the variance. Okay, so theta 1 has mean and the variance, and theta 2 has its own mean and the variance, and theta 3 has its own mean and variance. Okay, so if we have a specific parameters, then we have a distribution like this, and then the likelihood is actually calculating how likely the samples are coming from this distribution. For example, in this graph, we have 5 samples here. And then if we change the parameters for the Gaussian distribution, then we can come up with many distributions. So in this graph, I'm just showing 3 examples, 1, 2, 3. Okay. And out of these 3, which one is more likely than the others? Which means these samples are probably coming from this distribution rather than this or this, right? So that's more likely. That's likelihood function. Again, if we fix these parameters at a certain value, then we can define the distribution function exactly, and then we can calculate the probability of these samples. For example, if we assume these green distributions here, and then if we have 5 samples, then the probability looks like this. We have a probability here and here and here and here. So all of these 5 samples are not likely. Okay, but if we assume that these parameters are like this, and then we assume this distribution, and then these samples are a lot more likely coming from this distribution. Okay, so that's what a likelihood function does. Okay, so maximum likelihood estimate is the estimated parameters maximizing the likelihood function, and it's very intuitive and dominant in statistics. So let's start talking about the likelihood with a specific example, especially with the Gaussian distribution. Okay, with the Gaussian distributions, first we have to define the likelihood, and the likelihood looks like this. So basically, in general, the likelihood is this one. So probability of all the x's given the parameters. Okay, and the samples are independent. Okay, so n samples are independent, so we can use this product. Okay, now this one is about just one sample. Okay, and then so we assume that this probability distribution is Gaussian. So instead of just p, we use normal distribution here. And instead of theta, we have mu and sigma squares. Okay, then given these specific values, then let's assume that this is our distribution. And if we have samples like this, and this one is not likely. So if we draw some random samples from this distribution, if the sample is here, this one is not likely, but it's possible, but not likely. This one is a lot likely. So we can get these samples around here more likely. In this distribution, what we want is to update these parameters to increase the likelihood of all the samples. Okay, so we have to maximize the equation by updating these parameters. And before talking about the updating, we have one more thing, which is log functions. Because log function is a monotonic function, so it doesn't change the parameters. I mean, when the function is maximum, then we can get the maximum likelihood estimate. And when we apply the log function, but it doesn't change the maximum likelihood estimate. Even though the function value will be different. So it makes the likelihood equation much simpler. That's the reason why we take this log function here, especially when the distribution is based on the exponential family, like Gaussian distribution. Gaussian distribution has exponential function there, and if we take a log function, then the equation will be much simpler and easier. Okay, so originally this is what we do for the maximum likelihood. So this is likelihood, and we want to maximize by changing the parameter theta, and that is theta hat. Okay, you know the difference between the max and the arg max. So max is the maximum value, and arg max is the parameter that maximizes the function. Okay, so this one is about the parameter which maximizes the function, this one. And then if we take a log, then this one is not changing. Okay, maximum value is changing, but the parameter is not changing. So this one is Gaussian distribution. The estimate is here. And if we take the log, then it looks like this. So this one is not changing. So when the theta hat is here, we got the maximum. Likewise, even after this log function, when the theta hat is here, we got the maximum. And given n samples, this is what we want. Okay, so we apply the log function and to the likelihood. This one is actually px given theta, right? When we have a log and product, then we can have sum and log. Okay, so now we will focus on this. Now let's calculate the MLE for Gaussian. And from the previous slide, we want to use a log function. Okay, and this is log likelihood. And instead of x, then we can use each sample here, and then we have a sum. Okay, then if you remember the Gaussian distribution equation, by applying log, we have this term here, and this part is here, and since we have a sum goes into this. Okay, so this is our log likelihood function for Gaussian distribution. So it's a simple. In terms of sigma square, we have one sigma square and another sigma square here, and for mean we have mean here. Okay, and to get the MLE, the approach is quite simple. Just take a derivative, and the derivative should be 0. Okay, then that's how we get MLE for Gaussian. Okay, if we take a derivative and set it to 0, then the MLE mean is like this, and the MLE sigma square will be like this. And the MLE mean is minimum variance unbiased estimator. We are gonna see why we say it is unbiased. Then the MLE variance is biased with minimum variance. Okay. Now let's calculate. Okay, to estimate the mean, we take a derivative with respect to mean and set it to 0. Okay, and then if you look at this equation, this term and this term have nothing to do with mean. So when we take a derivative, then we just cancel. And let's focus on this term. And this 2 is going forward and cancel each other. And now we have 1 over sigma square. And that's it. And then this one is 1 over sigma square. Sigma xn is 1 over sigma square mu. And actually we can multiply sigma square both sides, so we just cancel. And then the mu is actually, here is constant, so this one is actually n times mu, and then we have a sum here. So if we move this one to this side, then this one is our MLE estimate. And about the variance, we do the same thing. So in this case, the sigma square is one variable, okay? We don't just use a sigma, okay? Sigma square is just one variable. And then this one has nothing to do with the sigma square, so we just cancel. And for this one, we have this one. And for this term, we have this one, and set it to 0. And then we rearranged the terms, and then we got this one. So this one is MLE variance. Okay, in the previous slide, the samples are scalar. So we talked about the univariate Gaussian distribution. Now, when the x is a vector, then the mean should be vector and the variance should be covariance matrix. We use the same thing here. We apply the log function to the multivariate Gaussian, so it looks like this. Okay, and then to estimate the mean, then it's almost same as before. And then to estimate the variance, we need a little trick. So we have to take a derivative of a determinant. Okay, then we do the same thing, and following these equations, finally we got this one. Okay, this is MLE. Before I said the MLE estimator for mean is unbiased, but the variance estimator is biased. So I'm going to show you why. Okay, so we take expectation of this estimator. Okay, and then this one was actually this one from the previous slide. So we just we calculate the expectation of this term, and the expectation can come into this summation, and then we have this term here, and this is tricky part. So this is expectation of one sample, and the expectation of one sample is actually the mean. Okay, so the sum over mu is n times mu, and we have 1 over n here, so they cancel each other. So finally we got mean. So this equation says when we take expectation of this estimator, then it is actually true mean. Okay, so it is unbiased. But when we calculate the expectation of this variance estimator, then if we follow this, then this is what we got. So if you look at this side and this side, okay, when we take an expectation, then it is not exactly sigma square. So it is biased. Okay, actually the expectation is smaller than the true variance. Actually, we have inequality here. So actually unbiased variance estimator for variance is like this. So we multiply n over n minus 1 to MLE estimator for a variance. Then this is actually unbiased variance estimator for variance. So it looks like this. So sometimes, even in Excel file, when we calculate variance, sometimes we use 1 over n, or sometimes we use 1 over n minus 1. So if we use 1 over n minus 1, it is unbiased. But if we use 1 over n, this one is maximum likelihood estimator. You might get confused with this biasness, unbiasedness, so let me explain what biasness means here. Okay, as I said, maximum likelihood estimator is related to overfitting, and it is biased to the samples. That's what overfitting means in general. And so we have an example here. So let's say we have 3 sets of 2 samples. So we have 2 samples here, and we have 3 sets. So let's look at these sets. So if we calculate the mean with these 2 samples, then mean would be around here. Okay, and if we calculate the mean with these 2 samples, then mean would be around here. And if we calculate the mean here, then mean is here. Okay, this one is estimator for the mean. Okay, and then we have 3 estimators. If we take an average, then probably it will converge to this one. Okay, it's unbiased. But if we check the variance, so let's say with these 2 samples, if we calculate the variance, then the variance will be like this. And with this one, If we calculate the variance, then the variance will be like this. And with this one, variance will be like this. But the true distribution looks like this. That's why we have samples here and here and here. Okay, so in the true distributions, the mean is here and the variance looks like this. So variance is quite large. But with the two samples, when we find the maximum likelihood estimator, then the mean is here, then variance is here, and the mean is here, variance is here, and mean and variance. And then when we take an average of these three, then the mean is converging to the true mean, but the variance, let's take an average of this variance, then probably the average will be like this, which is way much smaller than true variance. MLE mean changes with different sets. Okay, so here and here and here. So expectation converges, actually becomes mu itself. But sigma square ML does not change if the distance is the same. In this case, we use some specific types of samples here. But if the distance is the same, then the sigma does not change. Okay, then expectation will be this one. So it's the same as just MLE variance, MLE estimator, and this expectation is smaller than sigma square. So each MLE is kind of overfitted to the samples. That's the limit of maximum likelihood estimator.